Everybody, so we are back to our videos here. We've got just finished the SR Latch NAND version. We're now going to do the SR Latch with enable. Now I've kind of created this little dotted box section down here, and that's because this right here is what we just did up above. So the way I kind of designed this, we've got our S and R, and then we've got this S prime, R prime. So when we look up Q, we don't have to really analyze the circuit. S prime, R prime, we could just look up here and find out what the Qs will be. Um, so that'll help us out a little bit when we're going through the design and hopefully make it a little quicker. So we always want to do this basically a bottom-up style design, or what's called object-oriented, where you keep adding new features onto a base design. So let's start by taking a look at this new enable. And as you can kind of guess from the way I've done it here, if I've got enable equal to 0, now a 0, remember, into a NAND is going to force a 1. Doesn't matter what the other value is. 0 into a NAND will force a 1. We don't even need to find out what the second value is that's in here. So S and R are irrelevant. That's why those X's are there. And if we have two ones means to hold. So probably shouldn't have put this here because this is actually not as important on what the output is. You know, what really matters here is that this is going to hold whatever the previous values were. So we sometimes do this. I don't know if I'm going to be able to draw this. Actually, let me see if I can put a text thing here. So we sometimes call these the old values. Okay, I'm not sure why it's not. There you go. We sometimes use the lowercase q to distinguish between the two that's on here. But anyway, Q stays the same, Q prime. Maybe for the moment, I'll just do Q, just to let you know we're holding our own values. With like a little bit of a space there. Okay, that looks better. Okay, so 0 on enable forces a hold. That's kind of the end of the interest of the enable. Now we're going to come in and we'll put a 1 into enable. Now that no longer is going to force the output here. So now imagine our S for a sec is 0. And again, a 0 forces a 1. Make R equals 0. And a 0 will force a 1. So we still end up with the 0, 0 here, essentially with the 1 here. For just an AND, if you were to block out that for a sec, 1 and S is going to give you S. Negated will give you S prime. So essentially, when this becomes a 1, this is just an inverter for S. Same thing's going to happen for R because it's an identical circuit, just with a different input name on. So essentially, whatever's here is going to flip, which is what we see with the 0 to a 1. So if we put in a 0, 0, it becomes S prime 1, R prime 1, which does another hold. Now, if we go and it's enable and we have 0, 1, so S is 0 and R is 1. Good job. Okay, S is 0, oh, sorry, R is 1. Again, this is going to function like an inverter, so R prime is going to become 0. So 1 and 1 negated 0. A 1, 0 on S prime R prime, we can just look it up here. 1, 0 did a reset. That's just like our original, the NOR version interpretation of S and R. That's why it's very helpful to call these S prime and R prime, because it allows us to deal with the outer part of the enable. In which case that means we're essentially going to do, right, 1, 0 does a reset, which means I get, a 0 and a 1, and it is a reset. Now we can do S is equal to 1 and R is equal to 0. Okay, so if S is 1 and R is 0, and these act like inverters because enable's on, so I end up with S prime is 0 and R prime is 1. And I can look up S prime 0, R prime 1, which gives me a 1, 0 on the output. I guess I could write that in here, which means I get a 1, 0 here. Hey, it worked for me. Okay. And we get a set. So now we've got kind of our next function. And it's nice because I can control when I want it to happen. If I don't want these to happen, I just turn enable off, and it's irrelevant what happens to SR. My 1, 1, that's going to be my danger zone. So remember, if I went to 1, 1, these act like inverters, so I get zeros and 2 zeros, S prime, R prime on zeros, gives me this 1, 1. Oops. Which is my illegal state. It's illegal because it's going to make next time I go back to any of the holds, including the enabled version. Let's now have a very easy way to go back to hold with that enable. Just turn enable off, and it'll go metastable. So essentially, this just sets up a danger spot that we don't want to allow. So the disallowed version on an SR latch with enable is all 1s on the input. So now we've got our next, this is kind of an important building block, because if you look at the regular SR latch, there was no indication of time. You change S and R and it changes these. It has memory, it'll hold for an indefinite period, but it doesn't matter when you change them. So it's sequential, but it's not synchronous. So an SR latch is an asynchronous sequential logic. The enable allows me to make times when it can't change. So it can't change when enable is equal to 0. And so, that's kind of a crucial aspect to us, that enable is basically gets periods of time when it won't work. We're going to want to do one more upgrade, and now having this enable as kind of like a partial clock, we'll be able to add a full clock afterwards. So we've got one more thing, which will be called a D-latch. Technically an enabled one, but we usually just call it a D-latch. And then we can move on to doing a true flip-flop, which is what we're going to want for real memory.